Today we are going to learn about how to calculate various algorithmic complexity, that is time and the space complexity, with the one of the most basic algorithm for searching known as binary search. In binary search, you will be given array of numbers which are sorted in ascending or descending order. And these are the number indexing from 0 to 14. Now I will find out the middle term which is 0 plus 14 by 2, and that is 7. The element present at the 7th position is 53, and now I will compare the 53 with the element to be searched, that is 33, and the 33 is less than 53, so I will discard this part of array and focus on this part of array. And now again I will calculate the middle term, which is 0 plus 6 divided by 2, that is 3. The element present at third position is 25. Now again I will compare the middle term with the element to be searched, that is 33, and now it is greater than 25, so I will discard this part of array and focus on this part of array. Now again I will find out the middle term. 4 plus 6 divided by 2, that is 5. The element present is 43, and again I will compare with 33, which is less than 43, so I will discard this part of array and focus on this part. And now we obtain the element which we have to search. So the important point to note here is that each time we search for the given number, we discard half the part of array. So this is the recursive algorithm of binary search. In this algorithm we have passed the two arguments, that is x and k. X is the index of the middle term and k is the element to be searched. If x is equal to null or key of x equal to k, then return x. That is, if index of the middle term is equal to null, then this function will return null, and if the middle term element present at the middle term is equal to k, that is element to be searched, then it will return the index of the middle term. And if k is less than key of x, that is the element to be searched is less than the middle term, then it will search in the left side of the array, otherwise it will search in the right side of the array. And this two statement, bst search left of x comma k and bst search right of x comma k, call this function recursively, and this leads to the recursive call of this function. And this is the preview or the review of the binary search, and now we will focus on our main issue, that is how to calculate the time and the space complexity for the binary search. Let us define that the number of the comparison made to search an element in the array is t of n. As we have already seen that each time we made an attempt to search an element in the array, we discard half of the element. That is, we search the element in the n by 2 of the array. And if the number of the comparison made made in the BST search x comma k is t of n, then the number of the comparison made by the BST search left of x comma k will be t of n by 2, and then the number of the comparison made by the BST search right of x comma k will also be t of n by 2. And now let us assume that the time consumed by this statement will be 1 unit, and also the time consumed by this statement will also be 1 unit. If this is the case, we can write a recurrence relation, that is t of n is equal to t of n by 2 plus 2. That is the sum of the time consumed by this and this statement, that is 1 plus 1, that is equal to 2. This is the recurrence relation, and now we have to solve this recurrence relation to obtain the time complexity of this algorithm. Relation, we will substitute n by 2 in place of n, so we will obtain t of n by 4 plus 2 plus 2, and in the next step again we will replace n by n by 2, so we obtain t of n by 8 plus 2 plus 2 plus 2. Each time we substitute n by 2 in place of n, an increment of 2 is seen. So in next step again we will replace n by n by 2, so we obtain t of n by 2 to the power 4 plus 4 into 2. If we will keep going like this, then we will reach to the kth step, and kth step is like this. t of n by 2 uh, n by 2 की power k plus k into 2. Um, to solve to solve this equation, for simplicity we assume that n is equal to 2 की power k. So we substituted n is equal to 2 की power k in this equation. So t of n by 2 is equal to t of 1 plus k into 2. And now k is equal to log of n to the base 2. So we obtain the this equation by multiplying the logarithmic function on both the sides of this equation. So when we substituted k equal to log n in this equation, we obtained t of n by 2 equal to c1 plus 2 log of n to the base 2. The c1 is obtained because t of 1 implies that the time consumed when the number of the element to be searched is when the number of the element in the array is 1. So we obtain this equation, and so big O is equal to log of n. This relation is very important. This relation is the running time complexity of the binary search algorithm. Now we will calculate the space complexity for the program. To calculate the space complexity of a recursive program is very tricky, as lot of things happen behind the scene. To calculate the space complexity, we need to know how the memory requirement of a program grow with the input. This is the memory of the computer, and this memory is divided into the partition, and these are the various units of the memory. Generally we have the main method. This main method will first occupy the space in the memory. This main method will further call the bst7, 33. I have used bst in place of bst search for simplicity. This BST 7, 33 will occupy the memory of the computer. Roll back a bit. When a method is in the memory, the local variable and the information about the local variable associated with it will also occupy the memory of the computer. So this main method will call bst7, 33, and this bst7, 33 will occupy the space in the memory, and this bst7, 33 will again call the bst l7, 33, and this bst l733 will again call bst r3, 33, and this bst r3, 33 will again call bst l4, 33. And now this recursive tree will not grow, as the element to be searched is obtained. The space occupied by this recursion is equal to the space occupied by its function call stack. The space occupied by the function call stack is maximum when we are at the bst l4, 33. When we are at the bst l4, 33, the rest all bsts are also consuming memory, and this is the function call stack of this recursion. Now the space complexity is directly proportional to the maximum depth of the tree, and the maximum depth of the tree in this case is the length of the longest path in the tree, which is n in this case. So the space complexity is directly proportional to n. Space complexity is equal to big O of n. When we analyze any algorithm, we always take upper bound for the space or the time taken. So in this case, space or the memory consumption. Space is directly proportional to n, or we can also say that space complexity is equal to big O of n. So in general, space complexity of a recursive program is of the order of maximum depth of the recursion tree. So this was the space and the time complexity of binary search. Hope you understand the concept. This is all about binary search. In this tutorial, we have seen how to analyze an algorithm which uses divide and conquer, and also how to solve an recurrence relation. Hope you enjoyed this video. If you enjoyed this video, do not forget to press like button and do leave your comments.